We begin with the application of the Gauss's law. Here, we want to study, we have to find the electric field due to a spherically symmetric charge distribution. As you see here, we don't have any metallic or conducting object. It's just a symmetric charge distribution. In this case, the charges are distributed at any point inside the sphere. I draw the sphere. This sphere has a capital radius r, and with q, total q, capital Q, positively charged. Q is positive. Now I want to calculate the electric field at each point in the space. I take one example as a point, let's say a point B, okay? And in the next step, I want to calculate at the point C inside the object. Let's begin. Let's start with the point B. Okay, I want to calculate at this point the field created by the sphere. Here, first of all, we have to write bisymmetric we select a sphere. You know, in the case of a sphere, we choose a sphere as the Gaussian surface. We select a sphere of radius r, small r, as the Gaussian surface. As we have to calculate the field as a point B, and B exists outside the sphere, let's take point B at here. So R is greater than capital R. Okay, let's draw this sphere. Okay, this sphere, this one is a Gaussian surface, and it has a radius. We can choose a radius, we can say to the point B, which is equal to small r. Okay, as you see in this case, that small r is here we can write r is greater than the capital R. Okay, as you see. Here we have a positive charge, so the field created by the sphere is outward. We can draw. Here we have E. Okay. You know that the general equation of the flux by using Newton's law, Gauss's law, equals to E dot dA equals to Q n divided by epsilon 0. Okay, and here's the integral about a closed surface. you know that this Gaussian surface is closed around the sphere. It's important. It's important to put this circle on the integral. It means that's a closed surface. You know, this part of the equation related to the Gaussian surface. And Qn is related to the charge inside Gaussian surface. Okay, it's important now. I want to calculate these values now. You know that dA here, and we said before this term relates to and we said before that this term is related to Gaussian surface. This one. And Qn is related only to the charge inside the Gaussian surface. This one. We can write here phi equals to integral E. Here we have, I am calculating at the point B, okay? And here we can take a small element at this point. A must be, as a vector, must be perpendicular to the small element, and it has the same direction with E. So E dA here equals to integral E dA cosine 0. It's important to write this one. That's the angle between dA and E equal to 0. You know about the conditions. We have to write the conditions here. E must be constant at any point on the surface. It's important to write this condition. The second condition, E must be parallel with dA for each small element, and E must be radial. Okay, I forgot to write these conditions at the beginning of this problem. So E is constant. We can say phi equals to E integral dA equals to EA. Okay, this is about the Gaussian surface. Equals to Qn over epsilon. Okay, let's continue here. Now, this one is R. Now, the total flux equal EA equals to Qn divided by epsilon. Here we have a volume charge distribution, because we said that it's not a metallic object. In this case, we have a charge at any point inside the object. Okay? We can say this one is Qn. In this case, we can write Qn equals to rho times Vn divided by epsilon. And Vn, we can say A equal A for the Gaussian surface. A equals to 4 pi r square, and Vn concerning the charge equals to 4 over 3. Here we have a radius equal to capital R pi r cube. Okay, we substitute A by its value and Vn here. We get E equals to rho divided by epsilon 0. Vn equals to 4 over 3 pi r cube, and A equals to 4 pi r square. Don't forget that A is the area of Gaussian surface and Vn is the volume of Qn. Okay, we can cancel pi and pi, 4 and 4. We get the final form of this equation formula, rho r cube divided by epsilon r square. Okay, let's write this equation. We can say if r is greater than the capital R, E equals to rho r cube divided by epsilon 0 r square. Okay, now I want to draw this value on a diagram xy like this. Here we have x and y, and y we have the field, and x I'm talking about the distance. Okay, here we have distance. From I am studying here the case, okay, we can say here r. Okay, in this case I take here we have the capital radius, here we have the center, this center O is here. From here to here we have we can say we have this sphere, it's like this with the radius r, and we are working from r small is greater than this point. I am calculating here in this point. We calculated E equals to rho r cube divided by epsilon 0 r square. In this case, we see that E is inversely proportional to r square, and it's positive. So at any point here, this value must be like this. Okay, like this. The value of E equals to rho r cube divided by epsilon r square. We can use this formula for any point of r greater than the sphere. Maybe we can find here or here or here. All these points exist at a position out of the sphere. Out of the sphere. Let me now, I want to calculate the electric field inside the sphere. Okay? We do a new graph. As you see here, I want to calculate the field at a point. Let me see, as a point C. In this case, the position of this point must be less than r. Okay, here we have the capital R, and here we can see as a position small r. In this case, we have to say bisymmetric. Okay, the same thing. We have to say here by. Okay, we don't need to repeat the same thing because we said this before. Okay, just we can begin the calculation without repeating the conditions. Just we can draw the sphere. The sphere must be, we can say like this. Okay. Okay. This one is Gaussian surface. Okay. And the blue sphere has a capital Q. And I want to calculate the field at the point C. Okay. At this point, you know that the electric field is out. Okay. We can say out. At C is out. At any point must be out. Okay. Here. Okay. Here we have, from here to here, we have small r, and r is less than capital R. Okay, what we have to say, I want to write the equation of the flux equals to E dot dA, okay, equals to Q n divided by epsilon 0. Here, be careful. This one relates to the Gauss's surface. I mean to this surface. And Qn is the charge inside the Gauss's surface. Okay, inside, it's here. So here we have Qn. Here you have Qn inside the Gaussian surface. Here. Okay. We can write Qn equals rho times V n divided by epsilon. And E dA, also dA at this point has the same direction as the point C. Here we have dA at this point C, and E have the same direction. We can say E A E dA times cosine angle equal rho V n divided by epsilon 0. Okay, E is constant at any point, so EA equals to rho V n over epsilon. You know A is for the Gauss's surface. It's here, this one. This one has A equal 4 pi r square. Okay, so E times 4 pi r square equal rho divided by epsilon. Vn is the volume of the total Qn. It's not a shell. It's a solid object, solid Q object. Its volume equals to 4 over 3 pi r cube. The radius of this one from here to here equal to small r. Okay, we can calculate now its value. We can cancel 4 pi, 4 pi, r square left here r. We can say E equals to rho divided by epsilon 3 and r. Okay, we write the result here. If r is less than the capital R and greater than 0, okay, we can say E equals to rho divided by 3 epsilon 0 times R. As you see here, we can erase these lines. This is a linear relation between E and R. So we can draw this relation here, R less than capital R and greater than 0. The relation is linear, like this. Okay, which is equal E equals to rho R divided by 3 epsilon 0. And R, in the case of R greater than the capital R, here we don't have a linear relation, as you see. This is a simple example about the calculation of the electric field if we have a uniform charged sphere. Okay, the charges are distributed uniformly inside the object. In the next videos, we can do some calculation about a conducting object, for example, or we can also do some application about the shells. If we have a shell metallic or not metallic, and we can do the calculation of the electric field at any position, inside, outside the shell. Okay, I think it's all about this subject.